Border Gateway Protocol is a standardized exterior gateway protocol designed to exchange routing and reachability information between autonomous systems on the Internet. The protocol is often classified as a path vector protocol, but is sometimes also classed as a distance vector routing protocol. The Border Gateway Protocol does not use interior gateway protocol metrics, but makes routing decisions based on paths, network policies and/or rule sets configured by a network administrator. The Border Gateway Protocol plays a key role in the overall operation of the Internet and is involved in making core routing decisions. BGP may be used for routing within an AS. In this application it is referred to as Interior Border Gateway Protocol, Internal BGP or iBGP. In contrast, the Internet application of the protocol may be referred to as Exterior Border Gateway Protocol, External BGP or EBGP. BGP is the successor to the Exterior Gateway Protocol. BGP is currently the most widely used exterior gateway protocol by Internet service providers. BGP was originally designed to help transition from the core ARPANET model to a decentralized system that included the NSFNET backbone and its associated regional networks. The current version of BGP is version 4 codified in RFC 4271 since 2006. Early versions of the protocol are widely considered obsolete and are rarely supported. RFC 4271, which went through more than 20 drafts, is based on the earlier RFC 1771 version 4. The RFC 4271 version corrected a number of errors, clarified ambiguities and brought the RFC much closer to industry practices. Version 4 of BGP has been in use on the Internet since 1994. The major enhancement in version 4 was support for classless inter-domain routing and use of route aggregation to decrease the size of routings. Most Internet service providers must use BGP to establish routing between one another. Therefore, even though most Internet users do not use it directly, BGP is one of the most important protocols of the Internet. Compare this with Signaling System 7, which is the inter-provider core call setup protocol on the PSTN. Very large private IP networks use BGP internally. An example would be the joining of a number of large OSPF networks where OSPF by itself would not scale to size. Another reason to use BGP is multi-homing a network for better redundancy either to multiple access points of a single ISP or to multiple ISPs. Operation: BGP neighbors, called peers, are established by manual configuration between routers to create a TCP session on port 179. A BGP speaker sends 19-byte keep-alive messages every 30 seconds to maintain the connection. Among routing protocols, BGP is unique in using TCP as its transport protocol. When BGP runs between two peers in the same autonomous system, it is referred to as internal BGP. When it runs between different autonomous systems, it is called external BGP. Routers on the boundary of one AS exchanging information with another AS are called border or edge routers or simply EBGP peers and are typically connected directly, while iBGP peers can be interconnected through other intermediate routers. Other deployment topologies are also possible, such as running EBGP peering inside a VPN tunnel, allowing two remote sites to exchange routing information in a secure and isolated manner. The main difference between iBGP and EBGP peering is in the way routes that were received from one peer are propagated to other peers. For instance, new routes learned from an EBGP peer are typically redistributed to all other iBGP peers as well as all EBGP peers. However, if new routes were learned on an iBGP peering, then they are re-advertised only to all other EBGP peers. These route propagation rules effectively require that all iBGP peers inside an AS are interconnected in a full mesh. Filtering routes learned from peers, their transformation before redistribution to peers or before plumbing them into the routing table is typically controlled via route maps mechanism. These are basically rules which allow to apply certain actions to routes matching certain criteria on either ingress or egress path. These rules can specify that the route is to be dropped or, alternatively, its attributes are to be modified. It is usually the responsibility of the AS administrator to provide the desired route map configuration on a router supporting BGP. Extensions negotiation. During the peering handshake, when open messages are exchanged, BGP speakers can negotiate optional capabilities of the session, including multi-protocol extensions and various recovery modes. If the multi-protocol extensions to BGP are negotiated at the time of creation, the BGP speaker can prefix the network layer reachability information it advertises with an address family prefix. These families include the IPv4, IPv6, IPv4/IPv6 virtual private networks and multicast BGP. Increasingly, BGP is used as a generalized signaling protocol to carry information about routes that may not be part of the global Internet, such as VPNs. Finite state machines. In order to make decisions in its operations with peers, a BGP peer uses a simple finite state machine that consists of 6 states: idle, connect, active, open sent, open confirm, and established. For each peer-to-peer session, a BGP implementation maintains a state variable that tracks which of these 6 states the session is in. The BGP defines the messages that each peer should exchange in order to change the session from one state to another. The first state is the idle state. In the idle state, BGP initializes all resources, refuses all unbound BGP connection attempts and initiates a TCP connection to the peer. The second state is connect. In the connect state, the router waits for the TCP connection to complete and transitions to the open sent state if successful. If unsuccessful, it starts the connect retry timer and transitions to the active state upon expiration. In the active state, the router resets the connect retry timer to 0 and returns to the connect state. In the open sent state, the router sends an open message and waits for one in return in order to transition to the open confirm state. Queue messages are exchanged and, upon successful receipt, the router is placed into the established state. In the established state, the router can send receive, queue update, and notification messages to from its peer. Idle state, refuse all incoming BGP connections, start the initialization of event triggers. Initiates a TCP connection with its configured BGP peer. Listens for a TCP connection from its peer. Changes its state to connect. If an error occurs at any state of the FSM process, the BGP session is terminated immediately and returned to the idle state. Some of the reasons why a router does not progress from the idle state are: TCP port 179 is not open. A random TCP port over 1023 is not open. Peer address configured incorrectly on either router. AS number configured incorrectly on either router. Connect state, waits for successful TCP negotiation with peer. BGP does not spend much time in this state if the TCP session has been successfully established. Sends open message to peer and changes state to open sent. If an error occurs, BGP moves to the active state. Some reasons for the error are: TCP port 179 is not open. A random TCP port over 1023 is not open. Peer address configured incorrectly on either router. AS number configured incorrectly on either router. Active state, if the router was unable to establish a successful TCP session, then it ends up in the active state. BGP FSM tries to restart another TCP session with a peer and, if successful, then it sends an open message to the peer. If it is unsuccessful again, the FSM is reset to the idle state. Repeated failures may result in a router cycling between the idle and active states. Some of the reasons for this include: TCP port 179 is not open. A random TCP port over 1023 is not open. BGP configuration error. Network congestion. Flapping network interface. Open sent state, BGP FSM listens for an open message from its peer. Once the message has been received, the router checks the validity of the open message. If there is an error, it is because one of the fields in the open message does not match between the peers, for example, BGP version mismatch, MD5 password mismatch, the peering router expects a different MIAS, etc. The router then sends a notification message to the peer indicating why the error occurred. If there is no error, a QPALEAVE message is sent, various timers are set and the state is changed to open confirm. Open confirm state, the peer is listening for a QPALEAVE message from its peer. If a QPALEAVE message is received and no timer has expired before reception of the QPALEAVE, BGP transitions to the established state. If a timer expires before a QPALEAVE message is received, or if an error condition occurs, the router transitions back to the idle state. Established state, in this state, the peers send update messages to exchange information about each route being advertised to the BGP peer. If there is any error in the update message, then a notification message is sent to the peer, and BGP transitions back to the idle state. If a timer expires before a QPALEAVE message is received, or if an error condition occurs, the router transitions back to the idle state. BGP router connectivity and learning routes. In the simplest arrangement, all routers within a single AS and participating in BGP routing must be configured in a full mesh. Each router must be configured as peer to every other router. This causes scaling problems, since the number of required connections grows quadratically with the number of routers involved. To alleviate the problem, BGP implements two options: route reflectors and BGP confederations. The following discussion of basic update processing assumes a full iBGP mesh. Basic update processing: a given BGP router may accept NLRI updates from multiple neighbors and advertise NLRI to the same, or a different set, of neighbors. Conceptually, BGP maintains its own master routing table, called the lock rib, separate from the main routing table of the router. For each neighbor, the BGP process maintains a conceptual ADJ ribbon containing the NLRI received from the neighbor, and a conceptual ADJ rib out for NLRI to be sent to the neighbor. Conceptual, in the preceding paragraph, means that the physical storage and structure of these various tables are decided by the implementer of the BGP code. Their structure is not visible to other BGP routers, although they usually can be interrogated with management commands on the local router. It is quite common, for example, to store the two ADJ ribs and the lock rib together in the same data structure, with additional information attached to the rib entries. The additional information tells the BGP process such things as whether individual entries belong in the ADJ ribs for specific neighbors, whether the peer-neighbor route selection process made received policies eligible for the lock rib, and whether lock rib entries are eligible to be submitted to the local router's routing table management process. By eligible to be submitted, BGP will submit the routes that it considers best to the main routing table process. Depending on the implementation of that process, the BGP route is not necessarily selected. For example, a directly connected prefix, learned from the router's own hardware, is usually most preferred. As long as the directly connected route's interface is active, the BGP route to the destination will not be put into the routing table. Once the interface goes down, and there are no more preferred routes, the lock rib route would be installed in the main routing table. Until recently, it was a common mistake to say BGP carries policies. BGP actually carried the information with which rules inside BGP-speaking routers could make policy decisions. Some of the information carried that is explicitly intended to be used in policy decisions are communities and multi-exit discriminators. Route selection: the BGP standard specifies a number of decision factors, more than are used by any other common routing process, for selecting NLRI to go into the lock rib. The first decision point for evaluating NLRI is that its next hop attribute must be reachable. Another way of saying the next hop must be reachable is that there must be an active route, already in the main routing table of the router, to the prefix in which the next hop address is reachable. Next, for each neighbor, the BGP process applies various standard and implementation-dependent criteria to decide which routes conceptually should go into the ADJ ribbon. the neighbor could send several possible routes to a destination, but the first level of preference is at the neighbor level. Only one route to each destination will be installed in the conceptual ADJ ribbon. This process will also delete, from the ADJ ribbon, any routes that are withdrawn by the neighbor. Whenever a conceptual ADJ ribbon changes, the main BGP process decides if any of the neighbor's new routes are preferred to routes already in the lock rib. If so, it replaces them. If a given route is withdrawn by a neighbor, and there is no other route to that destination, the route is removed from the lock rib, and no longer sent, by BGP, to the main routing table manager. If the router does not have a route to that destination from any non-BGP source, the withdrawn route will be removed from the main routing table. Per neighbor decisions, after verifying that the next hop is reachable, if the route comes from an internal peer, the first rule to apply according to the standard is to examine the local preference attribute. If there are several iBGP routes from the neighbor, the one with the highest local preference is selected unless there are several routes with the same local preference. In the latter case, the route selection process moves to the next tiebreaker. While local preference is the first rule in the standard, once reachability of the next HOP is verified, Cisco and several other vendors first consider a decision factor called weight, which is local to the router. The route with the highest weight is preferred. The local preference, weight, and other criteria can be manipulated by local configuration and software capabilities. Such manipulation is outside the scope of the standard but is commonly used. For example, the community attributes is not directly used by the BGP selection process. The BGP neighbor process, however, can have a rule to set local preference or another factor based on a manually programmed rule to set the attribute if the community value matches some pattern matching criterion. If the route was learned from an external peer, the per neighbor BGP process computes a local preference value from local policy rules and then compares the local preference of all routes from the neighbor. At the per neighbor level, ignoring implementation-specific policy modifiers, the order of tie-breaking rules is, prefer the route with the shortest AS path. An AS path is the set of AS numbers that must be traversed to reach the advertised destination. AS1, AS2, AS3 is shorter than AS4, AS5, AS6, AS7. Prefer routes with the lowest value of their origin attribute. Prefer routes with the lowest multi-exit disk value. Before the most recent edition of the BGP standard, if an update had no multi-exit disk value, several implementations created a MED with the least possible value. The current standard, however, specifies that missing MEDs are to be treated as the highest possible value. Since the current rule may cause different behavior than the vendor interpretations, BGP implementations that use the non-standard default value have a configuration feature that allows the old or standard rule to be selected. Decision factors at the lock rib level. Once candidate routes are received from neighbors, the lock rib software applies additional tiebreakers to routes to the same destination. If at least one route was learned from an external neighbor, drop all routes learned from iBGP. Prefer the route with the lowest interior cost to the next HOP, according to the main routing table. If two neighbors advertise the same route, but one neighbor is reachable via a low bitrate link and the other by a high bitrate link, and the interior routing protocol calculates lowest cost based on highest bitrate, the route through the high bitrate link would be preferred and other routes dropped. If there is more than one route still tied at this point, several BGP implementations offer a configurable option to load share among the routes, accepting all. Prefer the route learned from the BGP speaker with the numerically lowest BGP identifier. Prefer the route learned from the BGP speaker with the lowest peer IP address. Communities. BGP communities are attribute tags that can be applied to incoming or outgoing prefixes to achieve some common goal. While it is common to say that BGP allows an administrator to set policies on how prefixes are handled by ISPs, this is generally not possible, strictly speaking. For instance, BGP natively has no concept to allow one AS to tell another AS to restrict advertisement of a prefix to only North American peering customers. Instead, an ISP generally publishes a list of well-known or proprietary communities with a description for each one, which essentially becomes an agreement of how prefixes are to be treated. Examples of common communities include local preference adjustments, geographic or peer type restrictions, DOS avoidance, and AS prepending options. An ISP might state that any routes received from customers with community XXX 500 will be advertised to all peers, while community XXX 501 will restrict advertisement to North America. The customer simply adjusts their configuration to include the correct community, ES, for each route, and the ISP is responsible for controlling who the prefix is advertised to. The end user has no technical ability to enforce correct actions being taken by the ISP, though problems in this area are generally rare and accidental. It is a common tactic for end customers to use BGP communities to control the local preference the ISP assigns to advertised routes instead of using MED. It should also be noted that the community attribute is transitive, but communities applied by the customer very rarely become propagated outside the next hop AS. Extended communities. The BGP Extended Community attribute was added in 2006 in order to extend the range of such attributes and to provide a community attribute structuring by means of a type field. The extended format consists of 1 or 2 octets for the type field followed by 7 or 6 octets for the respective community attribute content. The definition of this extended community attributes is documented in RFC 4360. The IANA administers the registry for BGP extended communities types. The extended communities attributes itself is a transitive optional BGP attribute. However, a bit in the type field within the attribute decides whether the encoded extended community is of a transitive or non-transitive nature. The IANA registry therefore provides different number ranges for the attribute types. Due to the extended attribute range, its usage can be manifold. RFC 4360 exemplarily defines the 2-octet AS-specific extended community, the IPv4 address-specific extended community, the opaque extended community, the root target community, and the root origin community. A number of BGP CoS drafts also use this extended community attribute structure for inter-domain CoS signaling. Uses of multi-exit discriminators, MEDs, defined in the main BGP standard, were originally intended to show to another neighbor AS the advertising AS's preferences to which of several links are preferred for inbound traffic. Another application of MEDs is to advertise the value, typically based on delay, of multiple AS that have presence at an IXP, that they impose to send traffic to some destination. Multipath BGP, an extension to BGP, is the use of multipathing. This typically requires identical MED, weight, origin and AS path, although some implementations provide the ability to relax the AS path checking to only expect an equal path length rather than the actual AS numbers in the path being expected to match to. This can then be extended further with features like Cisco's DMS Link BW, which enables a ratio of traffic sharing based on bandwidth values configured on individual links. Message header format. The following is the BGP version for message header format. Marker included for compatibility, must be set to all ones. Length, total length of the message in octets, including the header. Type of BGP message. The following values are defined: open, update, notification, keep alive, route refresh. BGP problems and mitigation. Internal BGP scalability. An autonomous system with internal BGP must have all of its iBGP peers connect to each other in a full mesh. This full mesh configuration requires that each router maintain a session to every other router. In large networks, this number of sessions may degrade performance of routers, due to either a lack of memory, or too much CPU process requirements. Route reflectors and confederations both reduce the number of iBGP peers to each router and thus reduce processing overhead. Route reflectors are a pure performance-enhancing technique, while confederations also can be used to implement more fine-grained policy. Route reflectors reduce the number of connections required in an AS. A single router can be made a route reflector, other routers in the AS need only be configured as peers to them. Confederations are sets of autonomous systems. In common practice, only one of the Confederation AS numbers is seen by the Internet as a whole. Confederations are used in very large networks where a large AS can be configured to encompass smaller, more manageable internal ASs. Confederations can be used in conjunction with route reflectors. Both confederations and route reflectors can be subject to persistent oscillation unless specific design rules, affecting both BGP and the interior routing protocol, are followed. However, these alternatives can introduce problems of their own, including the following: route oscillation, suboptimal routing, increase of BGP convergence time. Additionally, route reflectors and BGP confederations were not designed to ease BGP router configuration. Nevertheless, these are common tools for experienced BGP network architects. These tools may be combined, for example, as a hierarchy of route reflectors. Instability: the routing tables managed by a BGP implementation are adjusted continually to reflect actual changes in the network, such as links breaking and being restored or routers going down and coming back up. In the network as a whole, it is normal for these changes to happen almost continuously, but for any particular router or link, changes are supposed to be relatively infrequent. If a router is misconfigured or mismanaged, then it may get into a rapid cycle between down and up states. This pattern of repeated withdrawal and re-announcement, known as route flapping, can cause excessive activity in all the other routers that know about the broken link, as the same route is continuously injected and withdrawn from the routing tables. The BGP design is such that delivery of traffic may not function while routes are being updated. On the Internet, a BGP routing change may cause outages for several minutes. A feature known as route flap damping is built into many BGP implementations in an attempt to mitigate the effects of route flapping. Without damping, the excessive activity can cause a heavy processing load on routers, which may in turn delay updates on other routes, and so affect overall routing stability. With damping, a route's flapping is exponentially decayed. At the first instance, when a route becomes unavailable and quickly reappears, damping does not take effect, so as to maintain the normal failover times of BGP. At the second occurrence, BGP shuns that prefix for a certain length of time. Subsequent occurrences are timed out exponentially. After the abnormalities have ceased and a suitable length of time has passed for the offending route, prefixes can be reinstated and its slate wiped clean. Damping can also mitigate denial of service attacks. Damping timings are highly customizable. It is also suggested in RFC 2439 that route flap dampening is a feature more desirable if implemented to exterior border gateway protocol sessions and not on interior border gateway protocol sessions. With this approach, when a route flaps inside an autonomous system, it is not propagated to the external ASs. Flapping a route to an EBGP will have a chain of flapping for the particular route throughout the backbone. This method also successfully avoids the overhead of route flap dampening for iBGP sessions. However, subsequent research has shown that flap damping can actually lengthen convergence times in some cases, and can cause interruptions in connectivity even when links are not flapping. Moreover, as backbone links and router processors have become faster, some network architects have suggested that flap damping may not be as important as it used to be, since changes to the routing table can be handled much faster by routers. This has led the RIPE Routing Working Group to write that with the current implementations of BGP flap damping, the application of flap damping in ISP networks is not recommended. If flap damping is implemented, the ISP operating that network will cause side effects to their customers and the Internet users of their customers' content and services. These side effects would quite likely be worse than the impact caused by simply not running flap damping at all. Improving stability without the problems of flap damping is the subject of current research. Routing table growth. One of the largest problems faced by BGP, and indeed the Internet infrastructure as a whole, is the growth of the Internet routing table. If the global routing table grows to the point where some older, less capable, routers cannot cope with the memory requirements or the CPU load of maintaining the table, these routers will cease to be effective gateways between the parts of the Internet they connect. In addition, and perhaps even more importantly, Larger routing tables take longer to stabilize after a major connectivity change, leaving network service unreliable, or even unavailable, in the interim. Until late 2001, the global routing table was growing exponentially, threatening an eventual widespread breakdown of connectivity. In an attempt to prevent this, ISPs cooperated in keeping the global routing table as small as possible, by using classless inter-domain routing and route aggregation. While this slowed the growth of the routing table to a linear process for several years, with the expanded demand for multi-homing by end-user networks, the growth was once again superlinear by the middle of 2004. A full IPv4 BGP table as of May 2014 is in excess of 500,000 prefixes. Route summarization is often used to improve aggregation of the BGP global routing table, thereby reducing the necessary table size and routers of an AS. Consider AS1 has been allocated the big address space of 172.16.0.0/16, this would be counted as one route in the table, but due to customer requirement or traffic engineering purposes, AS1 wants to announce smaller, more specific routes of 172.16.0.0/18, 172.16.64.0/18 and 172.16.128.0/18. The prefix 172.16.192.0/18 does not have any host, so AS1 does not announce a specific route 172.16.192.0/18. This all counts as AS1 announcing 4 routes. AS2 will see the 4 routes from AS1, and it is up to the routing policy of AS2 to decide whether or not to take a copy of the 4 routes or, as 172.16.0.0/16 overlaps all the other specific routes, to just store the summary, 172.16.0.0/16. If AS2 wants to send data to prefix 172.16.192.0/18, it will be sent to the routers of AS1 on route 172.16.0.0/16. At AS1's router, it will either be dropped or a destination and reachable ICMP message will be sent back, depending on the configuration of AS1's routers. If AS1 later decides to drop the route 172.16.0.0/16, leaving 172.16.0.0/18, 172.16.64.0/18 and 172.16.128.0/18, AS1 will drop the number of routes it announces to 3. AS2 will see the 3 routes, and depending on the routing policy of AS2, it will store a copy of the 3 routes, or aggregate the prefixes 172.16.0.0/18 and 172.16.64.0/18 to 172.16.0.0/17, thereby reducing the number of routes AS2 stores to only 2, 172.16.0.0/17 and 172.16.128.0/18. If AS2 wants to send data to prefix 172.16.192.0/18, it will be dropped or a destination and reachable ICMP message will be sent back at the routers of AS2, because 172.16.192.0/18 would not be in the routing table. Load balancing problem. Another factor causing this growth of the routing table is the need for load balancing of multi-homed networks. It is not a trivial task to balance the inbound traffic to a multi-homed network across its multiple inbound paths, due to limitation of the BGP route selection process. For a multi-homed network, if it announces the same network blocks across all of its BGP peers, the result may be that one or several of its inbound links become congested while the other links remain underutilized, because external networks all picked that set of congested paths as optimal. Like most other routing protocols, the BGP does not detect congestion. To work around this problem, BGP administrators of that multi-homed network may divide a large contiguous IP address block into smaller blocks, and tweak the route announcement to make different blocks look optimal on different paths, so that external networks will choose a different path to reach different blocks of that multi-homed network. Such cases will increase the number of routes as seen on the global BGP table. One solution growing in popularity to address the load balancing issue is to deploy BGP Lisp gateways within an Internet exchange point to allow ingress traffic engineering across multiple links. This technique does not increase the number of routes seen on the global BGP table. Requirements of a router for use of BGP for Internet and backbone of backbones purposes. Routers, especially small ones intended for small home office use, may not include BGP software. Some SOHO routers simply are not capable of running BGP/using BGP routing tables of any size. Other commercial routers may need a specific software executable image that contains BGP, or a license that enables it. Open source packages that run BGP include GNU Zebra, Quagga, OpenBGPD, Bird, XORP and Viata. Devices marketed as Layer 3 switches are less likely to support BGP than devices marketed as routers, but high-end Layer 3 switches usually can run BGP. Products marketed as switches may or may not have a size limitation on BGP tables, such as 20,000 routes, far smaller than a full Internet table plus internal routes. These devices, however, may be perfectly reasonable and useful when used for BGP routing of some smaller part of the network, such as a Confederation AS representing one of several smaller enterprises that are linked by a BGP backbone of backbones, or a small enterprise that announces routes to an ISP but only accepts a default route and perhaps a small number of aggregated routes. A BGP router used only for a network with a single point of entry to the Internet may have a much smaller routing table size than a multi-homed network. Even simple multi-homing can have modest routing table size. CRFC 4098 for vendor-independent performance parameters for single BGP router convergence in the control plane. The actual amount of memory required in a BGP router depends on the amount of BGP information exchanged with other BGP speakers, and the way in which the particular router stores BGP information. The router may have to keep more than one copy of a route, so it can manage different policies for route advertising and acceptance to a specific neighboring AS. The term view is often used for these different policy relationships on a running router. If one router implementation takes more memory per route than another implementation, this may be a legitimate design choice, trading processing speed against memory. A full IPv4 BGP table as of May 2014 is in excess of 500,000 prefixes. Large ISPs may add another 50% for internal and customer routes. Again, depending on implementation, separate tables may be kept for each view of a different peer AS. Free and open source implementations. Simulators, BGP-LAY, an HTML widget that presents a graphical visualization of BGP routes and updates for any real AS on the Internet. SSFNET. SSFNET Network Simulator includes a BGP implementation developed by BJ Primor, CBGP, a BGP simulator able to perform large-scale simulation trying to model the ACEs of the Internet or modeling ACEs as large as Tier 1. BGP++, a patch integrating GNU Zebra software on NS2 and GTN-ETS network simulators. NSBGP, a BGP extension for NS2 simulator based on the SSFNET implementation. NetViews, a Java application that monitors and visualizes BGP activity in real time. Test equipment, systems for testing BGP conformance, load or stress performance come from vendors such as Ixia, Spirit Communications, Agilent Technologies. See also. References. Further reading, Chapter Border Gateway Protocol in the Cisco iOS Technology Handbook, external links. Cyclops ABGP Network Audit Tool by UCLA, BGP Best Path Selection in Cisco Device, Codenomic and Defensics for BGP, a test automation framework for BGP fuzzing and robustness testing, LinkRank A tool for BGP routing visualization by University of California, Los Angeles, BGP routing resources, BGP table statistics, BGP tables. A global BGP visibility analysis tool by Merit Networks, ACE number. Firefox extension showing the ACE number and additional information of the website currently open. RIPE routing information service collecting over 550 IPv4 and IPv6 BGP feeds at 14 sites around the world. RIS looking glass into the default free routing zone of the Internet. RIS providing IPv4/IPv6 address to BGP AS origin mapping. RIS BGP LAY BGP routing visualization tool by Universität Egli Study Romata, Linux Magazine. Demystifying BGP. BGP config generator. Free web-based tool to generate a Cisco Quagga BGP configuration. Some important BGP RFCs. RFC 4271, a border gateway protocol for RFC 4456, BGP route reflection, an alternative to full mesh internal BGP, RFC 4278, standards. Maturity variance regarding the TCP/MD5 signature option and the BGP4 specification, RFC 4277, experience with the BGP4 protocol, RFC 4276, BGP4 implementation report, RFC 4275, BGP4 MIB implementation survey, RFC 4274, BGP4 protocol analysis, RFC 4273, definitions of managed objects for BGP4, RFC 4272, BGP security vulnerabilities analysis, RFC 5492, capabilities advertisement with BGP4, RFC 5065, autonomous system confederations for BGP, RFC 2918, route refresh capability. For BGP4, RFC 1772, application of the border gateway protocol in the Internet Protocol using SMIF2, RFC 4893, BGP support for 4-octet AS number space, RFC 2439, BGP route flap damping, RFC 4760, multi-protocol extensions for BGP4. Obsolete RFCs, RFC 3392, obsolete, capabilities advertisement with BGP4, RFC 2796, obsolete, BGP route reflection, an alternative to full mesh iBGP, RFC 3065, obsolete, autonomous system confederations for BGP, RFC 1965, obsolete, autonomous system confederations for BGP, RFC 1771, obsolete, a border gateway protocol for, RFC 1657, obsolete, definitions of managed objects for the fourth version of the border gateway, RFC 1655, obsolete, application of the border gateway protocol in the Internet, RFC 1654, obsolete, a border gateway protocol for, RFC 1105, obsolete, border gateway protocol, RFC 2858, obsolete, multi-protocol extensions for BGP4. BGP interactions at router startup described as a sequence diagram, BGP protocol service level traffic variations mu dynamics dead link, BGP route reflection troubleshooting,